Hello learners, welcome back on the class of soil and rock mechanics. So I hope you all are safe and doing well. So in the previous discussion, I have discussed about the four various tests on the shear strength of soil. The first one is direct shear test or box shear test, and we have seen how to compute the shear parameter for the direct shear test. And after that, I will discuss another very important laboratory test, that is Tri-Axial Test. And with the help of Tri-Axial Test, we have computed the value of shear strength parameter either by using the formula relationship between sigma 1 and sigma 3, that is sigma 1 is equal to sigma 3 tan square alpha plus 2c tan alpha, or by drawing the Mohr circle and a common tangent drawn on the Mohr circle, that will be and the slope of that common tangent will give the angle of internal friction and intercept will give the cohesion. And the third approach to compute the shear strength parameter, that is PQ plot, in which we have drawn the PQ plot and we have computed the value of shear strength parameter. And after that, I have discussed a special case of triaxial test, that is unconfined compression test, and we have seen how to compute the value of shear strength parameter. And the last test we have discussed in the previous class, that is vane shear test, that is helpful in the laboratory as well as in the field also. So today I will discuss the Skempton pore pressure parameter, that is capital A and capital B, and how to compute the value of this Skempton pore pressure parameter. And I will also discuss the value for the different types of soil, and after that I will take problem on the Skempton pore pressure parameter. So today I am going to discuss about the pore pressure parameter. It is not possible to measure pore pressure by practical means. Then theoretical approach was given by Skempton. Pore pressure parameter represents response of pore pressure change due to change in lateral pressure and vertical pressure under undrained condition. And this pore pressure can be classified in two stages, like in the we have seen in the triaxial test, that is cell pressure stage and deviator stage. So the first Skempton pressure can be computed by cell pressure stage, and second pore pressure parameter is computed by the deviator stage or shear stage. So let us take pore pressure parameter, and this concept was given by Skempton. That's why it is also called Skempton pore pressure parameter. The pore pressure can be classified in two stages. The first is called cell pressure stage and the second one is deviator or shear stage. So first stage is cell pressure stage. The parameter capital B represents the ratio of change in pore pressure due to change in cell pressure. So pore pressure parameter B is the ratio of change in pore pressure divided by change in cell pressure. This is the Skempton pore pressure parameter named as capital B, where delta U is change in pore pressure due to change in cell pressure by delta sigma 3. That's why it is called delta U C. C for change in cell pressure. And this value of Skempton pore pressure parameter varies with different types of soil. Like value of B is equal to 0 when S is equal to 0, degree of saturation is 0, and we know that degree of saturation is 0 in case of dry soil. Similarly, B is equal to unity when our soil is fully saturated, when S is equal to 1, fully saturated soil. Now if I draw the curve of this B, so it is varies like that. Here B is equal to 1 and here B is equal to 0, S is equal to 0 and S is equal to 1. So this axis is degree of saturation, this value is B. Second Skempton pore pressure parameter can be computed by second stage or deviator stage or shear stage. So second stage is deviator stage or shear stage. In this stage, the parameter capital A is defined in terms of another parameter A bar, such that A bar is equal to product of A into B, and this A bar represents the ratio of change in pore pressure, change in pore pressure due to change in deviator stress. Deviator stress. So A bar represents the ratio of change in pore pressure to the change in deviator stage. So this A bar can be written as is equal to change in pore pressure, and this pore pressure is due to the deviator stress. So D divided by delta sigma D. And it can also be written as delta U D divided by delta sigma 1 delta minus delta sigma 3. So this is the A bar, and this A bar, the parameter A depends on the strain. The parameter A is the function of strain, degree of saturation over consolidation ratio and stratification of soil. So this A value depends on the strain, degree of saturation, over consolidation and stratification of soil. And the value of A may be negative. It may be as lower as minus 0.5 for over consolidated soil, and over consolidated soil is when OCR is greater than, over consolidation ratio is greater than 1, to as high as 3-4 very loose saturated sand. And we know that change in pore water pressure can be written as change in pore water pressure due to cell pressure stage, or due to change in cell pressure, and the change in pore water pressure due to change in deviator stress. So this delta change in pore water pressure can be written as, so delta UC can be written as B delta sigma 3, because we know that B is the ratio of change in pore water pressure due to the change in cell pressure divided by ratio of change in cell pressure. And similarly delta U bar sigma D can be written as A bar delta sigma 1 minus delta sigma 3. So this delta U can be written as B delta sigma 3 plus A bar can be written as A into B delta sigma 1 minus delta sigma 3. If I take B common, delta U is equal to B delta sigma 3 plus A times delta sigma 1 minus delta sigma 3. So this is the expression of change in pore water pressure, overall change in pore water pressure in terms of where A and B are the Skempton's pore pressure, Skempton's pore pressure parameter. So I am going to now discuss shear characteristics of soil. Shear characteristics of soil. Shear characteristics of soil. So for sand, if I draw the graph between the shear stress and shear strain, so on the y-axis it is shear stress, and on the x-axis it is shear strain. And this is for the, so these two are the shear stress versus shear strain curve. So this for the dense sand, and this is for the loose sand, and this is the maximum shear stress tau peak, and this maximum shear stress occurs at a 2 to 5% of shear strain, and the constant value of shear strain is 15 to 20% of shear strain. And this is also for the over consolidated soil, and this is for the normally consolidated soil. Similarly, if I draw the graph between volume change and shear strain, shear strain, so for dense sand and loose sand, this is the positive change in volume and this is the negative change in volume, and this axis is the shear strain. So for dense sand, the change in volume is decreasing up to certain shear strain, and once again it is increasing. As the shear strain increases, the value of change in volume is negative up to certain value of shear strain, and after that it will increases the change in volume. So this is for the dense sand, and it is for the loose sand, the value is constantly decreases. Change in volume is coming negative for the loose sand. Similarly, if I draw the pore pressure graph between pore pressure versus shear strain, pore pressure versus shear strain. So let us assume this is our shear strain, this value is positive change in pore water pressure delta U, and this is the negative change in pore water pressure. So this is for the loose sand. As the shear strain increases, the value of change in pore water pressure is positive in case of loose sand, and this is for the dense sand. U increases up to interlocking, and after that break. Once the interlocking break, then pore water pressure decreases in case of dense sand. Similarly, if I draw the graph between the void ratio versus shear strain, void ratio versus shear strain, so this axis is shear strain. Let us assume this is the initial value of void ratio. So on this side our void ratio is greater than initial void ratio, and below the E naught E is less than initial void ratio. So this is for the loose sand. And for the dense sand, once the void ratio decreases up to interlocking, and after that void ratio once again increases. So void ratio decreases and after that it will increase. So this is for the dense sand. E naught is the critical void ratio. It is that void ratio at which, so E naught is the critical void ratio. E naught is the critical void ratio. And what is critical void ratio? So it is the void ratio at which on shear disturbance there will be negligible or zero change in volume. So that void ratio is called critical void ratio. It is the void ratio at which on shear disturbance there will be no change in void ratio. So now I am going to discuss about the shear characteristics of clay. The behavior of saturated clay under drained or undrained condition is found different on conducting tri-axial test. So if I am interested to compute the shear stress or know the shear characteristics of clay, so we have to perform the tri-axial test. So firstly, saturated clays under undrained condition. So if UU test is conducted, it means clay is under undrained condition and loading rate is slow. The tri-axial test give the following result. So if UU unconsolidated undrained test is conducted, it means clay is under undrained condition and loading rate is slow, and the following result will come. So if I draw the Moore circle for UU test of clay, so this is the shear stress and this is the normal stress. So if I draw the Moore circle, so this is the Moore circle under UU test. A common tangent is drawn and the slope of this common tangent will give the angle of internal friction. In this case it is 0, and the intercept on the shear stress axis will give the undrained cohesion. This value is sigma 3, sigma 1, sigma 3 dash, sigma 1 dash, sigma 3 double dash, sigma 1 double dash, where Cu is the undrained cohesion and this Cu value is approximately 25 to 30 kilonewton per meter square for normally consolidated clay, and this value will increase 100 to 200 kilonewton per meter square for over consolidated clay, and phi u is equal to 0 for both normally consolidated clay and over consolidated clay. Second feature of the saturated clay, under drained condition. So I am going to show you what is the properties of saturated clay under drained condition. So drained condition is there. So CD test, consolidated drain test, is conducted on saturated clay, then result form for NCCR and so if I draw the Moore circle for saturated clay, so So the Moore circle for the saturated clay under CD test. This is the shear stress axis and this one is the normal stress axis. This is the Moore circle. So if I draw a common tangent on that, so slope of this common tangent will give phi d and intercept will give CD is equal to 0, and this test is for normally consolidated clay where CD is equal to 0 for drained condition, that's why it is called drained cohesion, and phi d is equal to drained angle of internal friction 20 to 30 degree, and these two value for normally consolidated clay. Similarly, if I draw the Moore circle for the over consolidated clay, so this is the shear stress axis and this one is the normal stress axis. This is the Moore circle. So this intercept will give the cohesion, drained cohesion, and slope of this common tangent will give drained angle of internal friction. And this is for over consolidated clay. And the value of CD, drained cohesion, is 6200 kilonewton per meter square, and drained angle of internal friction is 10 to 15 degree for over consolidated clay. So let us take one problem. An embankment 5 meter high having effective shear strength parameter, effective cohesion is equal to 50 kilonewton per meter square, and effective angle of internal friction is 16 degree, and the bulk unit weight of the soil is 16 kilonewton per meter cube. Skempton pore pressure parameter capital A is equal to 0.4 and capital B is equal to 0.92. We have to compute the shear stress of soil using effective stress parameter at the base of embankment if it is raised from 5 meter to 8 meter. Assume initially there was no pore pressure, and during construction pore water pressure does not dissipate, and it is given that at any depth lateral stress is half of the vertical stress. So we know that Skempton has given A bar is equal to change in pore water pressure in the deviator stress by change in deviator stress, and similarly B is equal to change in pore water pressure due to cell pressure, change in cell pressure by ratio of change in cell pressure. And we also know the expression delta U is equal to B delta sigma 3 plus A into delta sigma 1 minus delta sigma 3, and delta sigma 1 can be written as embankment height is changing from 5 to 8 meter, so it is 8 minus 5 into 16 is the bulk unit weight, so it is 48 kilonewton per meter square. And in the question it is given the lateral stress is equal to half the vertical stress, so 1 by 2 into 48, so it is 24 kilonewton per meter square. We know change in pore water pressure is B times delta sigma 3 plus A into delta sigma 1 minus delta sigma 3. B is given 0.92, delta sigma 3 is 24 plus A is 0.4, delta sigma 1 is 48 minus 24. So change in pore water pressure is 30.92 kilonewton per meter square, and this change in pore water pressure can be written as change in pore water pressure delta U is equal to final pore water pressure minus initial pore water pressure, and that is 30.92. Initial, there is a no pore water pressure is given, so UF minus 0 is equal to 30.92. so it is final pore water pressure is 30.92 kilonewton per meter square. Normal stress can be written as, effective terms, normal stress is sigma minus pore water pressure, and sigma is 8 into 16 minus pore water pressure is 30.92. so it is coming 97.08 kilonewton per meter square. So we know that according to Mohr-Coulomb equation, according to modified Mohr-Coulomb equation, shear stress is equal to C dash plus sigma n dash tan phi dash. Effective cohesion is 50 plus sigma n dash is 97.08 into tan 16. So it is coming, effective shear strength parameter is 77.837 kilonewton per meter square. So this is asked in the problem. So let us take another problem. The following results were obtained from a laboratory test, and the sample number 3 samples were conducted in the tri-axial test. For the first cell pressure 1 kg per meter centimeter square, deviator stress at failure is 2.02 kg per centimeter square, and the pore water pressure is 0.41 kg per centimeter square at failure. Similarly, for the second sample, cell pressure, deviator stress and pore pressure were measured, and for the third sample, cell pressure, deviator stress and pore water pressure at failure were measured. We have to compute the shear strength parameter using total stress analysis and effective stress analysis. So we know that firstly I will compute the shear strength parameter by total stress analysis. So in total stress analysis, we have the relation between the sigma 1, sigma 3, C and phi. Sigma 1 is equal to sigma 3 tan square alpha plus 2C tan alpha. Total stress analysis means we have to use the total terms, not the effective terms. So in first sample, total stress can be written as sigma 3 plus sigma d is equal to sigma 3 tan square alpha plus 2C tan alpha. And for the first sample, the cell pressure is 1 plus 2.02 is equal to 1 tan square alpha plus 2C tan alpha. So 3.02 is equal to tan square alpha plus 2C tan alpha. Let us assume this is equation first. Similarly, for the sample number 2, it can be written as 3.68 is equal to 1.5 times tan square alpha plus 2C tan alpha. This is equation number 2. And similarly, for the third equation can also be written as 2.37 plus 2 is equal to 2 tan square alpha plus 2C tan alpha. By the way, either using 1 2 or 1 3 or 2 3, the same result will come. So solving or we can write third equation also. 2 plus 2.37 is equal to 2 tan square alpha plus 2C tan alpha. So it is 4.37 is equal to 2 tan square alpha plus 2C tan alpha. So this is our equation number 3. Anyone you can operate. So operate 2 minus 1. So 3.68 minus 3.02 is equal to 2c tan alpha. 2c tan alpha is cancelled, so 0.5 tan square alpha. So here phi can be computed as 7.9 degree. Putting the value of phi, putting the value of alpha, that is 45 plus 7.9 by 2 in equation first. So we get 3.02 is equal to tan square 45 plus 7.9 by 2 plus 2c tan alpha. So the value of C is 0.74 kg per centimeter square. Now we have to use, so these are the C and phi is called shear strength parameter. This shear strength parameter we have to compute using effective stress analysis. So effective stress analysis. So in the effective stress analysis, this is sample sigma 3 means cell pressure. Similarly sigma d in kg per centimeter square. Sigma 1 is equal to sigma 3 plus sigma d can be computed. Pore water pressure is given. So sigma effective cell pressure sigma 3 is equal to sigma 3 minus pore water pressure, and similarly effective measure principal stress is sigma 1 minus u can be computed. So for 3 sample number 1, 2, 3, the value of cell pressure is 1, 1.5 and 2. Deviator stress is 2.02, 2.18 and 2.37. So sigma 1 can be 3.02, 3.68, 4.37. Pore water pressure is given in the question. Pore water pressure is 0.41, 0.62, 0.70. So the effective cell pressure is 3.02, 1 minus 0.41, so it is 0.59. Similarly 1.5 minus 0.62, so it is 0.88. 2 minus 0.7, so 1.3. Similarly measure principal stress 3.02 minus pore water pressure is 0.41, so it is coming 2.61, and similarly 3.06 and 3.67. Dear student, so we have discussed about the various shear strength tests like direct shear test or box shear test, tri-axial test, vane shear test, direct compression, unconfined compression test, and after that today I have discussed about the pore pressure parameter. And in the pore pressure parameter we have discussed about what is the Skempton pore pressure parameter and how to compute the Skempton pore pressure parameter. And this pore parameter, the value of pore pressure parameter varies on the types of soil and different properties of the soil. That is also I have discussed today. And after that I have taken one problem related to the pore pressure parameter, and in that problem we have seen how to compute the shear strength parameter in terms of effective terms. So with the help of this Skempton pore pressure parameter we have computed the change in pore water pressure, that is by relation delta U is equal to B delta sigma 3 plus A delta sigma 1 minus delta sigma 3, and with the help of that change in pore water pressure we have computed, and this change in pore water pressure is the final pore water pressure minus initial pore water pressure, and with the help of that pore water pressure computed. Once we have computed the pore water pressure, so effective normal stress is computed by normal stress minus pore water pressure, and after that we have applied the modified Mohr Coulomb equation and computed the effective shear strength parameter. In the second problem I have we have computed the shear strength parameter by total stress analysis and effective stress analysis, and we have seen the shear strength parameter by using the relationship between the measured principal stress and minor cell pressure and angle of internal friction and cohesion, and we have computed the shear strength parameter. So take care of your health and happy learning.